Start.
Big Wego and Indo classmate. Today, Kisendra, Dana, and me are going to present the application of combined function in real world. And for today, we're going to use animals as our main topic.
Animals.
Yeah. One of the animal behavior that relates to combined function is animal movement. And one type that the type of movement that animals have is some animals can run, some animals hang to tree, some animals can fly, and some animals can crawl. But basically, all these animals have arms and legs. But how about the animals that do not have arms and legs? For the main guest that we're going to use as our main topic is snakes. So how actually snakes relates to our topics? How actually their movement use the application of combining function. So for this part, I'm going to give to Dana to describe.
So I know you guys seem so like doing all the disgusting. Your face really show that you discuss all the snakes. But don't worry, after this we don't have any real snakes video or what. So the first, I'm just gonna keep on moving by just showing you some 3D animation of how does the snake move in real life situation. So as you all know, the snake moves in a sinusoidal movement, whereby they actually contract and relax their muscles in order to move, and their movement are actually their movement are the same as the sine graph that we learned before. So this is how we derive the video just now shows how we derive the graph that we're going to show later. So this is actually how the slow motion of the movement of the snake. So as you can see, the green arrow is actually the friction and the weight distribution of the snake when they move. And it also shows the contraction and the relaxation of muscles as I mentioned before. And the red dot here is actually the constant dot, whereby it indicates the midpoint of the snake's body. So here's the two graphs that we're going to show to you. The first one is actually the sinusoidal function, as we all know. So the graph is like this. We make it into two cycles. And oh yeah, for your information, the length of the snake is 64 centimeter. So we assume that the amplitude is 3, and therefore the maximum is 3 and the minimum is -3. And the equation is not clear here, but it's actually -3 sine pi over 10x. So the second one is actually the polynomial of linear function. So why does we choose a linear function here? Is because it shows the pathway, like the video just now. The snake glides from top to bottom. So we assume that it's a linear function. So Christina is going to talk about the key features of the graph.
Sorry, still excited. Okay, as you can see just now, the snake, he said was 64. Then you might be wondering why is it 40 here. It's because as the snake moves, as you realize, it goes up and up. The body does not move in a straight line. So if you take that into account, we since it's 64 and we actually read a few books and stuff like that, so we assume that the snake moves 3 here and 3 there. So the body contracts as it moves nearer, you know, like a centipede. Yeah, so it moves 3 and 3. So if you give that 3 and 3, you get 6 here. So you minus 1, 2, 3, 4, 5, 6, 7, 8. So it's 8
Times 3.
times 3, 24. 24 minus 64, which is the entire length, the straight line. You get a snake moving at this length. Okay, does it make sense? And it's 0 here because the snake's head is here. So it's here to here. And the linear function, there's a negative here because we assume that there's two arrows here, means it might make a circle because we all know the world is round. So you start back and then you begin, which is here. So, yeah.
So this is actually our combined graph from the sinusoidal and also the linear function. So the combined graph actually shows the real movement of the snakes if we see it from the top view. So the snake really glides like the way the snake glides. It's a sinusoidal function. So this is actually, like I say, the combined graph of both the function that we showed before.
So it's the path of the snake that you're talking about, right?
Yes, the path and also the movement.
But as we all know, that there's a lot of factors influencing nature. You don't get things the way they really look. Like what we presented just now will happen in a perfect world if there was no friction, or if a snake was what you see in cartoons. So, if you look closely at the snake's movement, which you'll see, if you're really scared of snakes and you really don't like snakes, I recommend you to close your eyes and imagine this part never happened.
It's only the short video clip.
Okay, if you see, the snake actually lifts up its body because the muscle contracts and it actually lifts the body up. Okay, so this is the digital way, a computerized picture of it.
Enough. When they added this to their model, it was right on.
Okay, you can see that as it lifts, the body actually goes up. It's higher than what we actually assumed just now. We said 3 and 3, but if you look at this image, it actually goes further up and it goes further down because it lifts up the body. So the assumptions that we have to make a perfect model, which if you actually did research, like we read a few papers on it, and it was actually, there's a lot of differentiation and integrations you have to do to get the exact model for it. So to get all of this, you actually have to take into account how much the snake lifts up its body. But it's really hard because some snakes lift more. It depends on the species. So it actually varies according to snakes. And the part changes according to its will. A snake does not necessarily want to move from A to B like we saw just now, one straight line. There might be rocks in between and trees and stuff like that. So it will adapt to situations. So that is also takes into account. And like I said earlier, the species and size plays a huge part trying to get the equation. And there we go. Thank you.
And then for the equation, what does the x stand for? What does the y stand for again?
It's the distance, like x is the distance between the snake itself, the wavelength, and y is the distance between horizontal distance.
Oh, it's actually the snake itself, right?
Yeah.
The vertical distance, vertical length and horizontal length. Alright. And then did you get this from somewhere, the equation, or you make up the
The
equation?
equation was
Assume.
we assume because the original one had a lot of differentiation and
So you minus off all the first. But was it similar, the actual one?
the actual one is really, really long. They didn't have a basic equation.
Oh.
Yeah. Because they actually used the equation to they wanted to create this robot to help in surgery.
Right.
So it's actually the application that we showed just now, the snakes. It's actually applied in the real world whereby they actually want to invent a robot to help in surgical method.
Okay. So did you cite the work? It's inside. Citation.
It's not at this point.
Okay, okay. Thanks.